Welcome to session 20 in our series on electricity and magnetism. During the last several sessions, we learned that alternating current is the electricity of choice for our production, transmission, and distribution systems. You recall what alternating current looks like when we graph it. It goes positive, 0, negative, 0, positive, back and forth on a regular pattern. And for the electricity that comes out of your wall at home, out of your outlets, it's 60 times a second that variation is occurring. Now, 50 to 55% of the electricity that's produced goes into driving motors. So what kind of motor can you use with electricity that's doing that? Why don't we start with a motor we're familiar with, the commutator motor. So if we feed alternating current into this, will it work? Well, it will, but there's some problems. Let's take a look at what the problems are. If we were to use a permanent magnet field, in other words, a constant magnetic field, while this is switching back and forth 60 times a second, we might have a problem. Let's take a look, a close-up of a small motor operating with that situation. So what I'm going to do is I'm going to use this alternator at a very slow speed. I'll turn it by hand, and we will produce a sine wave here, and you can watch this little motor right here with a little stick on it. You can watch how it behaves. Let's plug it in to the outlet, and here we go. I'm rotating that very slowly. We are at about 5 to 7 cycles per second. The motor's not spinning, it's just vibrating back and forth. And the faster I go, the faster the vibrations and the smaller the movement. And we're at about 30 cycles per second, and the motor's just sitting there vibrating. That's a problem. So how do we solve that problem? Well, for over 100 years, the way we solved it was by using an electromagnet for the field magnets. So if we feed the same electricity into both the field magnets, the electromagnetic field, and the part that rotates, then they switch back and forth simultaneously, and it behaves like a DC motor would. It doesn't care that this is flipping back and forth because this is doing it at the same speed, so the forces would always be in the same direction. You could reverse it by switching the leads between the two elements. So that's one solution. Pretty common. We still have lots of power tools that operate that way. Here's a cutaway of a corded drill. Here's the cord you can see. And I will spin this, and you can see the commutator spinning. And there's the electromagnet that's being used for the field. Almost an identical power drill with the cord. So a commutator motor, or commutator rotor, will work with alternating current if we use electromagnets for the field. But there's another alternative as well. If we could convert the alternating current to direct current, then this rotor would work just fine with a field that's produced by permanent magnets. Let's take a look at how that would work here. So we have alternating current, alternating voltage, and if we use diodes, remember what diodes do? They only let the electricity go in one direction. So if I use one diode, we end up with that, okay? Now if I use multiple diodes in a particular configuration, then I would then get these lower bumps, lower voltages, flipped over to this side. So I'm getting a lot more of my power available for the rotor. So we basically have a pulsating DC power, and this rotor would be just fine with a permanent magnet for the field. Let's take a look at how that works. We're going to use the same motor. We're going to use the same motor, and we're going to use the same alternator, except we're going to use the diodes that come with the alternator to power the little motor. I will plug this in to the direct current side and watch the motor and the oscilloscope. You notice it's all positive now, and the motor is just happily spinning. I can reverse that by changing the plug here. It doesn't matter which way I spin it, spin the alternator, it's the diodes that determine whether it's a plus or a minus. I'm going to switch this back again. Notice the little bumps on there. Why do we have those little bumps? Well, those are the peaks of the three phases. Those are the little peaks of the three phases. Still kind of sticking up past the average. So one of the motors we can use is the commutator motor under certain conditions. Diodes with permanent magnets as the field, or we use electromagnets for the field with AC. The field magnet has to have a core that's laminated just like the rotor. Remember, when we have rapid changes in the magnetic field, we can generate eddy currents which waste energy and they generate heat. Let's take a look. Let's go back to some basic stuff. Way back, I think it may have been session 3, and I took a little couple of double A's, and I could energize it, and the rotor would turn, and the thing we found though is I had to either make and break the circuit or sometimes reverse the direction of flow in order to keep the motor spinning. Well, we already have electricity that's kind of doing that, don't we? We have alternating current. It's already switching back and forth. Can we use that to drive a motor? Let's take a look. Now, I can't very well feed the 60 cycle AC into this because this is a pretty flimsy little motor. It cannot spin that fast. So what we have here is a permanent magnet for the rotor. There's the south pole in blue, there's the north pole in red, and down here is an electromagnet that's being fed with alternating current, 60 cycles per second. Now it's not self-starting, there's way too much inertia in that rotor for the strength of that electromagnet. So I'm going to have to give it a little kick to get it going. All right, here we go. So that's spinning at exactly 60 revolutions per second. Not 59, not 61, exactly 60 revolutions per second. It is the only speed that can spin at, because that's the rate that the electromagnet is switching north-south, north-south, north-south. Now, it will develop torque. If I load it, there's torque there. I can put some frictional force on that and it will load up. But if I overload it, it'll stop and I have to restart it. Not very convenient. Okay? This is called a synchronous motor because the rotor is synchronized to the frequency of the electricity that's feeding the electromagnet in the field. Notice there's no commutator. That's kind of nice because there's no brushes to make noise or wear out or a commutator to wear out. So that is an advantage. Until recently, synchronous motors were not very common. They had kind of niche applications. Factories had them for applications where maybe you wanted a very precise control of speed, didn't want it to change at all. They used the synchronous motor to do some power factor correction, which means if you've got your amps and your volts out of phase, which is very typical in alternating current, the synchronous motor helped bring them closer together. Other than that, it was not common. Let's take a look at what a more industrial looking synchronous motor would look like. Usually there were multiple poles, not just the two that I showed you. Let's take a look at what that might look like. Actually, it's going to be something you're kind of familiar with. That look familiar? I bet it does. Yeah, it's the alternator. The alternator that you have in your car is pretty much like a synchronous motor. First, let's review how the alternator worked. Remember, we have a rotor. It can either be permanent magnets, or in this case, it's an electromagnet that produces a north-south, north-south, north-south series of poles. Those poles produce a magnetic field pattern that kind of looks like that. That magnetic field cuts through the conductors of the stator. Let me get you in the middle here. Cuts through the conductors of the stator and generates electricity in the windings. These alternators, and the great big ones at power plants, are three-phase alternators. And you recall all that means is there are three separate windings spaced evenly around, and each of the windings gets its peak, the peak sine wave, in sequence. So as this rotates in there, we generate three sine waves. We call that a three-phase alternator. Now, let's get back to the motor business. So if we were to send electricity through this, let's start with just direct current or something. So here's direct current. I would have a distribution of magnetic poles. Red is north, blue is south. Now, if I feed three-phase alternating current into these windings, what happens is each of the phases becomes the strongest magnet in sequence. Okay, one of them will be peak, and then the next one will take the peak, then the next one will take the peak, and that will cause this to look like it's rotating. That will be the effect. These poles, the poles will appear to be moving around like that. Now, if we energize this electromagnet, or it could be permanent magnets already, north, south, north, south, if we have these sitting in here and they have a north pole here, lock onto a south pole here, all the way around, all these poles locking in to their opposite, this rotation will cause this rotor to spin. And it'll spin at that frequency that we're feeding into the stationary part. Let's do it. That'll make it a little clearer for you. Let's scoot this out of the way. This alternator is going to produce three-phase power. We're going to feed it into this alternator and get some torque out of it. Now, right now, it's not spinning because the magnetic field is rotating way too fast for the poles to lock onto each other. In order to get them to lock on, I'm going to use this cordless drill to get this up to speed. So now they have now locked onto each other, and it does produce some torque. Now if I grab it too hard, it will overload and it will stop. And I'll have to start it again. Whoops. Now you can see how inconvenient it would be to use a motor like this in our everyday applications, because every time you use it, you have to get it first up to speed and then engage it, okay? Which would be pretty bad for everything I can think of. Hand power tools, drills, saws, even a garbage disposal, you name it, and that's a problem. The problem is the power we're giving it is not matching what the motor is doing at a particular time, except that one speed that matches the frequency that we're feeding it. So the way to get around that is to use solid-state physics, digital circuitry, to sense and then have a sensor that tells us what is the motor doing, what is the speed that the motor is going, and I will now give the motor something it can use. Okay, so what we're going to use is this little digital circuit here. And I've got it already set up, and we're going to use a 12-volt battery. And let's watch right here. Started right up because the digital circuit knew that it wasn't turning. And now it knows exactly what speed it's going at, and if I want a higher speed, it won't just increase the frequency, it will sense what it's doing, how fast it's going, and carefully increase the frequency as the motor can handle it until it gets to what I've set it for. So the trick is to sense what the motor is doing and give it electricity it can really use. I think of this as an inside-out motor. The part that spins is on the outside, the part that's stationary is on the inside, and on the part that spins we have a set of magnets. You can see here where I've marked it in blue and red. Here's a south pole, north pole, south pole, north pole, south pole, north pole. It goes all the way around. On the inside are a bunch of coils of wire. It's a three-phase motor. So it's like, let's say this is phase 1, phase 2, phase 3, phase 1, phase 2, phase 3, and that continues all the way around. Those coils, all the phase 1s are tied together in series, all the phase 2s are connected in series, all the phase 3s are connected in series, and then they are connected like this. This represents all the phase 1s in series, all the phase 2s, and all the phase 3s, and then we're going to energize it across here, and across here. First I'm going to do this manually, kind of a real crude way. I'm going to power it. I'm going to hook up power to those two, and then these two, and then these two, and we're going to watch it rotate in steps. Kind of a crude digital power supply. I'm going to give it 12 volts, and here are my three leads, like the ends, the green, the red, and I didn't have a yellow. So here we go. Let's start this at the top and energize these in sequence. Okay, we got a quarter turn. But that's kind of what the digital circuits do. They provide those pulses, but they do it at exactly the right time with some kind of a feedback system. I'm now going to transfer these leads, supply leads, to that little digital control circuit, and we'll operate it like we did the alternator. All right, I think we're ready to go. Here we go. We'll start it up. And we can go faster, faster. I can crank it way up and it would know the position and increase the frequency appropriately. Okay. Well, I hope that was useful information for you. The reason I spent the time with the synchronous motor is because it is becoming very practical in many applications because of the way we can provide that feedback from the motor to the control circuitry, and then we can use it for all kinds of things. We can use it in power tools, we can use it in our fans for our heating and cooling systems, for pump systems, and we're using them in our electrical automobiles or our hybrid automobiles. So it's become a lot more useful. It can be a very practical way of converting electricity to mechanical energy. In our next session, we are going to take a look at a motor that is as common as the commutator motor in your home. It's called the induction motor. And the reason I didn't present the induction motor before I introduced the synchronous motor is the synchronous motor is probably a lot easier to understand. It's really kind of simple to see the poles interacting. Induction motor is a little bit more complex. So thanks for coming, and I'll see you next time.